All right, guys, welcome to lesson 2 or lesson 14 of Unit 2. Today we're going to talk about these things called slope fields. We're going to teach you guys how to sketch one, and also you're going to learn how to match a slope field to a differential equation that it belongs to. So, first of all, let's go ahead and explore a little bit here. So what we have here is we have a parabola. This is the graph of the equation y equals x squared, which I've got written over here on the left side. And as you guys may know, if we take the derivative of this, we would get 2x. And if you remember what the derivative represents, it represents the slope of your function at any given point. So for instance, if I wanted to find the slope of my parabola at the origin here, I would plug the x value for that point into my derivative. Now, if you were to plug 0 into the derivative, you're going to get 0. And what that means is that the slope at that point is 0. Do you guys remember what a 0 slope looks like? A 0 slope is a horizontal line. So the tangent line to the quadratic at this point would have a horizontal tangent line represented by that little blue line I just drew there. Okay? Say I wanted to find the slope at x equals 1. But x equals 1, I would get a slope of about 2. So here's the point where x equals 1. And I would have a slope of 2, so that'd be over 1, up 2, kind of be going in, I don't know, it's not a very good slope, but it's as good as it gets. There we go. I'm going to do that in red, actually. But our tangent line would be there. That's funny because this slope looks more to me like a over 1, up 1, but the slope should be 2 at that point. But oh well, we'll just pretend it's not. Maybe the graph is a little bit warped or something. But anyway, and we could just kind of keep doing that. We could find the slope at 2, and we could likewise sketch the slope at 2, and then at 3, which is way up here. And as you guys can see, the slopes are just getting steeper and steeper. And we could do the same thing on the left side too. Like I could find the slope here at -1. Find the slope here at -2. And I can find the slope here at -3. What you guys might notice is that if I were just to kind of go through and just sketch a whole bunch of slopes, don't they just kind of eventually just kind of trace the line? Kind of interesting, isn't it? So here's one interesting little fact I want you guys to take away from this. If you drew a tangent line at every single point for a given function, basically all those tangent lines put together, if you keep them kind of short and piece to piece, it'll basically just end up tracing the curve itself. Okay, so that's one interesting fact. Okay, now let's go ahead and work backwards here a little bit. So let's say that I don't know what the original function is, but I do know what its derivative is. So for instance, I know that the slope at x equals 0 is 0. So I would have a flat line there. But here's the thing about this, though, is that all we need to know is that x equals 0. Now there's a lot more places on this whole graph where x equals 0, like here equals x equals 0, here too. So technically, since I don't know where my function is located, any point where x equals 0 would have a 0 slope. Or maybe you remember how when we found the slope at 1, remember how that was a slope of 2? Well, once again, though, any point where x equals 1 is going to have a slope of 2. Likewise, over here, we had a slope that looks like this, but once again, that slope's just going to be the same for any place with the same x value. Okay, so we end up with that. Now, let's take a look at what's going on here, what I'm trying to demonstrate. when you integrate this function, right, you can get the original function, x squared, but it's x squared plus c. Now we already know what x squared looks like, right? But plus c, you guys might remember from pre-calculus or algebra, anytime you add a number to a function, it just shifts the graph up. So depending on what that c is, you could have a parabola just about anywhere here. So, as I mentioned before, when all you know is the derivative, then all we know is that at x, the slope is 0. But there's a lot of places where x equals 0. So there's a lot of places where the slope equals 0. And in the same way, we know that at x equals 1, the slope is 2. But there's a lot of places on this graph where the slope would be 2. And so all these little lines would be parallel. That's a nice little geometry fact for you in case you forgot. Remember, parallel lines have the same slope, right? So anyway, I'm just rambling at this point. But let's just say I were to find the slope at a whole bunch of points and just sketch them all. This is what it would look like. And this is what we call a slope field. Now, I don't know if you guys can tell, it's a little bit difficult to see it because they're everywhere, but if you just kind of follow the slopes, you get a parabola. There's one. Or maybe we could follow these slopes. And we'll talk about how you guys can sketch a line in there like that a little bit later. But for now, the point is that when you have a differential equation, that means it's an equation with a derivative in it, you can basically plug in the x value, and sometimes the y value if it's needed, if it's an implicit one, but usually just the x value. So if you plug in the x value, you can find the slope, and then you can kind of sketch that slope. And if you sketch it everywhere, you get what's called a slope field. And it traces out a shape of a function which matches what the general solution is. In this case, it's a parabola, a quadratic equation. Okay, and so that's what we call a slope field. Let's go ahead and formalize that with a definition. So what is a slope field? A slope field is a picture of the slopes of a general solution of a differential equation at various points in the xy plane. So back it up. It's a picture of all the slopes of a general solution. The rest of that definition it's the solution of this differential equation at various points in the coordinate field. So that is what a slope field is. It's a picture of all the slopes of a general solution of a differential equation at various points in the xy plane. All right. Now, before we go any further, I'd like you guys to pause the video here, and I would like you guys to match these lines with these slopes down here. Okay, so pause the video and see if you can match the slopes up correctly. Well, hopefully you guys recognize that the zero slope is that one because it's a flat horizontal line. Now, something else you might notice is that we have two positive slopes here, the half and the 2. Now, positive slopes slope in an upward direction as you move to the right. So that would be these, not that one. That one and this one. Those ones have positive slopes because they slope in an upward fashion to the right. Okay? Now, the one that is steeper would be the one that's bigger. So that's the steeper slope. And so that would be a slope of 2, whereas this one would be a slope of a half. Now, these other two slopes here and here, these are negative slopes. So those are the ones that are going to go with these ones here. And once again, the steeper one is going to go with the negative 2. And the half is that one. And then this guy here is an undefined slope. Undefined slope is a vertical line. It has no slope because the run is 0. And you guys know slope is rise over run, right? Well, if you have a rise over run and your run is 0, that means you have a 0 in the denominator. And for fractions, we call that undefined. It doesn't make sense. So a vertical line has an undefined slope. All right. So the reason I want to do that is because because of what we're about ready to do here. We're going to actually sketch a slope field. So what I'm going to do here is I'm going to give you guys a differential equation. Now this is an implicit differential equation. You know why it's an implicit differential equation? Because it doesn't have just an x in it, but it also has a y. That's what we call a implicit differential equation. Anytime the y is not by itself, if you have a y, then it's implicit. So this is an implicit differential equation. So what I want to do is I want to sketch the slope at every one of these dots on this field. And I don't know if you could tell, but there's actually some dots on the y-axis here and on the x-axis. We're gonna do quite a few of these. Now, you don't have to show all your work. It's kind of tedious. I'm going to show my work for some of them, but I'm not going to show my work for all of them. I mean, it's just kind of tedious. So let's go ahead and start with this point up here in this corner. Now, first of all, that point has the following coordinates. X is -2 and y is +2. So if I want to find my slope at that point, I'm going to plug it into my differential equation. So dy dx, -x, -y. I'm going to plug in the x value that I have up there for that point, and I'm going to plug in the y value up there that I have for that point. And you'll notice that the negatives cancel, and you're left with 4. So I have a slope of 4. Now, here's what I want you to notice. First of all, it's positive, right? So it's going to have an upward to the right slope. So as we go to the right, it's going to slope upwards. And 4 is actually a pretty big slope. So it's going to be a pretty steep line. So I would draw it like this. Now, we're not going to be that picky about just how steep you guys choose to make them, but they should be relative to each other. So what do I mean by that? Well, let's do the next one, and I think that'll help explain it a little bit. Go ahead and do this next point right here. Now that point is at -1, 2. Now if I plug in -1, 2, the negatives cancel, I'm left with 2. Now this is also a positive slope, right? But it's a smaller positive slope. So what that means is when I sketch the slope at this point, it's still going to go upwards, but I don't want it to be quite as steep as this, okay? So I would make it a little bit less steep. I don't want to go too far less because I may end up needing to make it even flatter. So, but we're just going to say right there, okay, that's a good slope of 2. And we're just estimating. We're just estimating. Now, if you want to get really picky about it, I mean, you can. You can start here at this point. You can go over 1, up 2, and connect your dots. But we don't need to be that picky, although you can. So what do I mean by relative? So remember I said you don't need to have the slopes exactly right. They just need to be accurate relative to each other. Well, that means when you compare them, they should match. So this was a slope of 4. This is a slope of 2. So we would expect this one to be steeper than this one. That's what I mean by relative. Compare them, it should be accurate. They should be accurate compared to each other. Let's go ahead and do another point here. Let's do this point right here. Now the coordinates for that point are 0, 2. If I plug in 0, 2, I get 0. So that's an easy one to draw. Just a flat line. Because we know that 0 slopes are flat like that. So basically all I'm doing is I'm picking the coordinates for each point, plugging them in to a differential equation, and that tells me what the slope is at that specific point, so I can sketch roughly what that slope would look like. All right, let's do another one. Let's do the next one to the right. So this point. That point is over 1 up 2, right? So over 1 up 2, I'm going to plug that in. So in this case, I'm going to get -1 times 2, which is -2. Now we had it 2 earlier, remember? It was a positive though. This is a -1. This is what my +2 slope looked like. So whenever you draw the negative one, once again, we want them to match, relatively speaking. And so since these slopes are the same, they're just opposite signs, I would want this slope to kind of be just about as steep as this one over here, but maybe, but obviously going in the different direction because it is a negative one. Okay, so I'm going to draw a line that's just going in the opposite direction, but pretty much the same slope, same steepness. It's just going in the opposite direction. You guys might not be too surprised to learn that if I plug in the next point, it's going to end up being -4. We're getting a little bit of symmetry here, and that's not uncommon when you do slope field. You start getting symmetry. So this one's going to match this one. It's just going to be in an opposite direction. I'll prove it for you. So that's over 1 up 2. Oh, I'm sorry, that's over 2 up 2. So now I'm going to plug in 2, 2, and I get -4. So it's going to have the same steepness as this purple one over here, but it's just going to be going in the opposite direction. So whenever I sketch that slope, it will look something like this. Now, I'm talking a lot and I'm writing a lot. It doesn't have to take this long. And so at this point, I'm just going to go ahead and go a little bit faster for the next row. And I'm going to start doing a little bit of mental math, and you guys can just kind of listen along with me and see if you agree or disagree. Hopefully agree, because I hope I don't do something wrong. But anyway, here we go. Let's do the next one. All right, so for the next point, right here, that one has the coordinates -2, +1. So that's going to give me a slope of 2, which means it's going to match the other pink line that I have up there, and I'm expecting that to end up just being parallel to this other one as well, just like that. Okay, next one, I'm going to go ahead and plug in the next point. Let's do blue this time. If I plug in this point, which is -1 and +1, I'm going to end up with a slope of 1. So now 1 is going to be slightly less steep than the pink line, a little bit flatter. And as we can predict, this is just going to be a reflection. And then once again, here in the middle, we're going to end up with a flat one again because we're going to plug in a 0, and that's just going to make the whole thing become 0. Okay. Now for the next row, every one of these points have something in common. Every one of these points have a y value of 0. And anytime you plug in 0, unless it's in the denominator, you're just going to get a 0 slope. So all of these points are just going to be flat lines, just like that. Matter of fact, anything on the x or y axis are just going to be flat lines because you're plugging zeros in. Okay. Now just be careful though. If you ever have a differential equation where it's a fraction and you plug a 0 in the bottom, that does not make 0. That makes undefined. That's a vertical one, so you got to watch out for that. The next thing I'm going to do is we're going to notice some more symmetry here. And once we kind of catch the drift of it, I think we can just kind of cheat and just use the symmetry of the shape to figure out the rest. So, for instance, if I were to go with this point right here, but you got to be careful with this because they're not always symmetrical in the way you think they would be. But in this case, if I pick the point -1, -1, if I plug that in, I'm going to end up with -1. So this was my 1 slope. So that's going to look the same. It's just going to be going in the opposite direction. It would be nice if when I click on the eraser, it actually turned into. All right. Don't get saucy, Mr. So there's that. And we can kind of predict what this other side's going to look like, right? We're kind of starting to get the picture here of what's going on. And so we can kind of start just cheating a little bit, I think. Got to be careful with that, but it's certainly a time saver. That next one be pink line there. There we go. And there we have our slope field. So basically, you just plug in some points, and after you've done a few, you start to notice some symmetry, and you can kind of take a swing at it and take a blind shot at it and see if you get the right answer. But there it is. That's the slope field. Okay? Now, we don't really have enough slopes here to get a good sketch of what this graph would actually look like. But you know what it looks an awful lot like to me? It looks like we're following a pattern where it's, wow, it's really it's steep up here, but it looks to me like it's probably going something like this, right? And as we get higher, it gets a little bit steeper, right? Down here, it's doing this. So, and what these different little beige lines are, you don't have to draw those. That's not part of the solution. So that tan line, you don't have to draw those. I want you to draw those on your graph right now because that's part of the solution. But just remember how I told you that basically the slope field sketches the curve of the particular solution or the general solution. So each one of these little tan lines represent a possible particular solution. We don't have an initial condition, so we don't know which one it is. But we'll get to that later. For now, all I wanted you guys to do was to get the slope field. Got some magical things popping up. All right. So now I want you guys to practice a couple of these. And I want you to kind of get used to doing it quickly and using the symmetry and stuff. So it says, see student handout. So it's not in the notes here. And I don't remember if I actually printed this out in your guys' handouts earlier this year. So if I didn't, you may want to print this out, or maybe just do a rough sketch on your own if you don't have a printer. But here they are. Go ahead and pause the video here really quick and see if you guys can get these things down. It'll probably take you a couple minutes because I have given you quite a few, but each one of these are a little bit different. Okay, so they're all worth looking at. And the more you do, the more you're going to get used to seeing what shapes tend to be. You're not going to do the student practice 2 yet. We'll get to that. Right now, you're just going to do the student practice 1. But like I said, let's go ahead and pause the video. Do as many of those as you can in the time provided. And then when you unpause the video, I will go over the solution. So here's your solution to number 1. Here's your solution to number 2. Notice the vertical lines here I have on the x-axis because that's where y equals 0. So when you plug 0 into the bottom, that's undefined, and an undefined slope is vertical. Then we have slopes of 1 all the way across here, actually negative 1, and positive 1 down here, and then negative halves up here and positive halves here. So there's that slope field. Let's go ahead and take a look at the next one. All right, so here's the answer, number 3. What's kind of interesting about this one is where the symmetry is at. You'll notice that the symmetry, instead of being vertical or horizontal, is actually diagonal. So all those slopes are 1, all these slopes were 0, all these slopes were negative 1, etc. I had a hard time getting my slopes to be relatively accurate over here. You know, this was a slope of 1, this was a 2, and then gosh, I couldn't make this steeper than 2 without making it not steep enough to where I had 4, and then without just making that vertical. So, but that's okay. I mean, when it gets to be that extreme, it just kind of gets difficult to tell anyway. So this one really looks weird. They're kind of like a little swirly shape, as you can see there. Kind of strange looking. All right, let's go ahead and take a look at the next one. You gotta love these ones. The slope is 1 no matter where you go. You can't plug anything in for x or y. The slope is always 1 at every point. You just have a whole bunch of slopes. Go ahead and take a look at number 5. And there's number 5. You'll notice that all the slopes are the same vertically. So all these were positive 1s, all these were positive 2s, all these were negative 1s, all these were negative 2s. Now, that's kind of important to talk about, actually. It's what our next part we're going to chat about is, why are they the same like this, vertically? Well, because there's only an x. So notice that every one of these points here have the same x value. The only thing that's different about those points is their y values. But as you can see, for the differential equation, the y value doesn't matter because it's not even there. So you have the same slope in the entire column. In the same way, earlier we saw something up here. I'll try to re-sketch it again here. I've already erased it. This one, notice how this one only had a y. Well, look at that graph again, and you may notice something. All the slopes in the same row are the same. Something like this. But notice that all the slopes in that row are the same. Why is that the case? Well, let's look at all these points. What do all these points have in common? Well, they all have the same y value of 1. The only thing that's different about them is that they have different x values. But my differential equation doesn't even care about x. So whenever you have all the same slope in the same row, that means your differential equation has just a y value. And in the same way, whenever all your slopes are the same in the same column, when all your slopes match in the same column, that means your differential equation only has an x value in it. And then finally, when you come over here, remember this one, they were the same everywhere. That's because it didn't matter what x or y was at all. So not only is it the same in every row, but it's also the same in every column because it doesn't have an x or a y. Okay, so that's an interesting little thing to note there. There we have it. So that's your first set, is how to sketch a slope field. That leads us into our next part. A really common question on the AP exam, other than sketching your own, which honestly it's not extremely common to sketch your own because not only is it extremely tedious and time consuming and not all that impressive to do it, but also they're kind of tricky to grade anyway because really the whole thing is just estimation. But they do ask those types of questions where you sketch the slope field. However, a more common thing I would say in the multiple choice section in particular is to match a differential equation with a slope field. And so based on the things that we just talked about, there's some common characteristics like the one we just said before. If the differential equation ever equals 0, that's where you would expect to see horizontal slope lines. So whenever you're looking at your equations and slopes and trying to match them up to see which one goes with which, just ask yourself, well, what's going to make this equation equal 0? Oh, well, that'll equal 0 if x equals 2. Okay, so let's look on our slope field and see which of these slope fields has a 0 slope when x equals 2, right? That's one thing you can look for. Here's another thing to look for. If your differential equation is positive, we would expect to see the lines going up, obviously, and if it's negative, we'd expect to see the lines going down. That's kind of like one of your last resorts to look at, though. Now, this is an important one, though. If your differential equation only has an x in it, as we said before, that means your slopes are all going to be the same vertically. In the same column, they'll all be parallel. Whereas if your differential equation only has a y value, that means all the slopes will be the same in the same row horizontally. They'll be parallel. Okay. The last thing is if you look at your differential equation, you find it's undefined somewhere. Look for which, slope field has undefined slopes at that point, obviously. Right? Some other notes here. A lot of times it helps to look at the slopes along the x-axis because that's where the variable is equal to 0. So that's kind of helpful. It's also helpful to know the shapes of the function families, but we'll look at that type of way of matching them a little bit more later on. So for now, what I really want you guys to be aware of is the following thing. This is a pretty important one. Do not like that a bit too large. So this is an important one. This is an important one. And this is an important one. These are going to be our first ones we're going to look at. We're going to ask ourselves, what I'm going to do is I'm going to give you guys a, well, let's see. I forget what the looks like. So here, I'm going to give you a slope field. And you should be able to tell me something about the differential equation based on this picture. And so here's what we're going to know. We're going to know that if all the slopes are the same vertically, in other words, they're parallel in the same row, that means the differential equation should only have an x. But if all the slopes are the same in the same row, horizontally, they're parallel, that would mean our differential equation only has a y. Okay? we can also look at our slope field and ask, okay, where does this slope field have a flat horizontal line? Well, then that should tell us something about the differential equation. So let's go ahead and take a look at that. Now, what I want to draw your guys' attention to for this one here is a couple of things. First of all, notice all the slopes are the same in each column. These are all parallel slopes. And whenever all your slopes in the same column are parallel, that means that there is only an x in the differential equation. Because no matter how high up you go, in other words, no matter what the y value is, it doesn't change the slope. So the y has no effect on the equation. Therefore, all the slopes in the same column are the same. So there's one thing I know. Here's another thing I know. I know that anytime we're on the y-axis, I have a zero slope. And what's significant about that is that's when x equals 0. So I know that my differential equation should equal 0 when x equals 0. Notice also we have negative slopes on the right side and positive slopes on the left. Okay, so if I plug in a negative x value, I should get a positive slope. How would that happen? That would happen if my equation had a negative in it already. So if when you plug in a negative, the negative in the equation cancels out the negative you plug in and you get a positive. So let's go ahead and take a look here. There it is. So you guys agree that if I plug in 0 for x, I should get 0 for my slope, and therefore all horizontal tangent lines. Here's another one. Notice that there's only an x. When we said there's only an x, all your slopes in each column should be parallel, which we have once again. And then once again, another thing you can look at is negative slopes are on the right side of the graph. So if you plug in a positive number for x, this negative turns it into a negative number, and that's why we have negative slopes on the right side and the opposite happening on the right. Let's take a look at another one here. What do we know here? Well, notice that the rows are the same, which means that it doesn't seem to matter what the x value is, because no matter how far over to the right or left you go, you always have the same slope. So that means x does not seem to be affecting the slope. But also, it's also the same vertically, which means y is not affecting it either. So actually, in this differential equation, I would not expect to see an x or a y. Also, this matches one of the examples we did earlier, where it was equal to just a number. And sure enough, there it is. So in other words, you guys should be able to look at one of these and just kind of know some things about it, okay? So this one looks an awful lot like one of the ones on your sheet too from earlier. The ones that have this shape are usually of the form x plus or x minus y or something like that. And there it is. But let's look at some things, right? Look at your slopes. This is where they're all 0. Now, what do all these points have in common? At all these points, the x and y values are the same. Like this one's 1, 1. This one's 2, 2. 0, 0. Negative 1, negative 1. Negative 2, negative 2. So it makes sense that when you subtract a number from itself, because they're the same, you get 0. Okay. So there's a couple of things there. But notice that, are all these slopes the same? No. It gets flatter as we move to the right. So that means x affects the slope. So x needs to be a part of the differential equation. How about in the columns? Are the columns all the same? Nope. Slope changes as we go up and down, which means that y seems to be affecting the slope, and therefore y also needs to be a part of the differential equation. So in this one, we have an x and a y, so we don't have that kind of vertical or horizontal parallelism going on. Here's another one. What do we notice about this one? I notice that the rows are the same, which means that the x values don't seem to be affecting the slope, which means that our differential equation should not have an x. Now here's something funny. There's nothing on these points. Sometimes they don't even put anything there if the slope's undefined. I would really like to put vertical lines myself to indicate that it's undefined. But technically, they don't put anything there if it's undefined, because you guys know undefined means it doesn't exist. But there's nothing wrong with drawing a vertical undefined slope. So, but as you can see here, we have only a y in it because the rows are the same. All right. So now here's the types of questions I would like you guys to be able to answer. You guys should be able to look at a slope field like this and use the characteristics of this picture to find out which one of these equations, which one of these differential equations go with that slope field. Okay. Now, first of all, notice something, that the columns are the same. Since all the columns are the same, that means the y value doesn't seem to be affecting the slope, and therefore it needs to be a differential equation without a y. So I know it can't be b, and it can't be c either. What else could it be? How about if we had, let's take after you look at your columns and your rows, notice my rows are different, right? We don't have parallel in the rows, so it has to have an x in it. But so after you look at your rows and after you look at your columns, the next thing you want to look for is you want to look for those zero slopes. So notice that all my zero slopes are on the y-axis. That means anytime x equals 0, the slope equals 0. Now that's not very helpful to me, unfortunately, this time, because if you plug 0 in here, yep, you get 0. But the same thing's actually true here. If you plug 0 into sine, you get 0. So that doesn't help. That doesn't separate the answers very much. Let's see. Let's plug in a number. Like, now I'm going to pick a funny number that I know works for sine. Let's go ahead and plug in pi. If I plug in pi, what do I get? Sine of pi is -1. Now pi is about 3.14. So we want to find on our x-axis where x is about 3.14. So 1, 2, 3. Here's 3.14 is here. So that's probably going to be a slope like this. Does that look like a -1 slope to you? And the answer is no. Positive slope. But this one down here, if you were to plug in a 3.14, well, you would just get 3.14, and that is a positive slope. So we know it's not the top one now. So sometimes you have to just pick a point and plug it in if your little quick tricks don't work. But like I said, start by looking at the rows, start by looking at the columns to see if it has only an x or only a y. Then after that, look at your zeros. And if that doesn't work, I say just pick a point and see if the slope is met. Okay, so let's go ahead and do some more here. Here's another one. So what do you guys notice about this one? What do we start off by looking at first? We start off by looking at rows and columns. So do you guys see parallelism in a row or a column? I see parallelism in a row. And when that happens, that means there's no x value in the equation. So it can't be this one and it can't be this one. Okay? After we look at rows and columns, what do we look at? We look for where the zero slopes are. So let's take a look at the zero slopes. Here's my zeros. So that seems to happen when y equals, I don't know what that would be, maybe 2? They're not numbers, so it's not very helpful. But so basically here it is. The slope equals 0 when y equals 2. Well, if I plug 2 in here, I get 6. But if I plug 2 in here, I get 0. So it's not that one. So once again, you start by looking at rows and columns to rule out if there's an x or a y, or maybe neither or both. And after that, you just look at your zeros. And in this case, that was enough. But if that's still not enough, then you just pick a random point and test it. All right, let's do another one. Now, hopefully you guys might already have an idea of which one this one is, because we've seen one that's shaped like this already. But let's take a look at it. First of all, do you notice how no rows are the same, and the columns aren't the same either? So this is a very asymmetrical looking graph. So since the rows don't have any parallelism and since the columns don't have any parallelisms, that means that this graph has both an x and a y in it. So I can eliminate this and I can eliminate this because it has to have both an x and a y. Now I've got to decide, is it x minus y or x plus y? Well, let's look at our zeros right here, for instance. That's going to be the point probably like 1, 1. Well, if you plug in 1 for x and 1 for y, you get 0 for that one. But if you plug in 1, 1 here, you get 2. Well, we should have a 0 slope at 1, 1, so that would be this guy. Okay? Once again, I'll say it again. You start with your rows, then you go to your columns, then you look at the zeros, and then you just test a random point. Another one. All right. I don't see any parallelism in the rows, but I do see them in the columns. So since we have parallelism in the columns, that means that y does not affect the slope, and therefore there's no y in the equation. So I can eliminate this. Ah, darn, that didn't eliminate very much. Let's look for some zero slopes now. I have zero slopes when x equals 0. If you plug 0 in here, you don't get 0. If you plug 0 in here, you just get 1. So that's not the answer. If you plug 0 in here, you do get 0. And if you plug 0 in here, you get 0. So now we're stuck between these two. So let's pick another point here. Once again, you want to pick something that works for sine. So let's do pi again. Now, as you guys know, we plugged in pi before and we got -1, right? If I plug in pi here, I get 3.14. Now that's helpful because this is a negative and this is a positive. So let's find a place on our graph where x equals 3.14. Well, here's 1, 2, 3. 3.14 is just going to be a little bit more over. So we're looking at these slopes right here. This is where x equals 3.14. Now, does that look like a positive slope or a negative slope to you? It's a negative slope, so it's not this one. It's this one. Now here's another thing we'll talk a little bit more about next time. You can also tell by the way that these slopes are going. It makes a wave, doesn't it? And that's a sine wave. Okay, and we'll talk a little bit more about that next time, but for now, the strategy we're using is good enough. So at this point, what I'd like you guys to do is work on the student practice number 2 on the handout. So let me bring that up really quick. For student practice number 2, you guys have 6 slope fields, and your job is to match these 6 equations to the ones they go with. So pause the video here and see if you can match the correct slope field to the correct equation. And remember, try to go through that strategy I shared with you. Rows, columns, zeros, random. Okay? Pause the video. When you unpause it, you'll have the solution. Okay, and there's your guys' solutions. What I did was I just started looking at my graphs here, and I found D is really obvious, right? That's the one where the slope is the same everywhere, and we know that one's just a number. That has to be number 11. The one that's just. The next thing I noticed was that for this guy here, all the slopes in the same row were the same, and that means this is a differential equation that only has a y in it. There's only one option that has that. It's A, so I knew that had to be A. After that, I remembered this weird-looking shape. Usually it's the one with the x minus or x plus y, and so I went with this. The next one I matched up was F. I was a little bit bothered here because it looks, if you look carefully, it looks like they have horizontal tangent lines here, and that's actually incorrect. They should have vertical ones here. But I did notice that they just, you might have also just thought they didn't put it. In which case I told you that means it's undefined. So it's undefined when y equals 0, which is on the bottom, and it's 0 when x equals 0, just put it on the top. So in that case, I knew that that one had to be F. So now I had A, then I had D, then I had F, C. So I just had B and E to choose from. Now, for those ones, just look at the slopes once again. For this one, we have 0 slopes on the y-axis. So anytime x equals 0, we would have a 0 slope. Well, in this case, that would be undefined, not 0. So I knew this one couldn't be b. All right. But anyway, there's your solutions for that. And I think that wraps up. You guys are like, I hope so, Mr. Brady. I've got other work to do. We'll leave that off for now. Well, I guess we could talk about it. It's not like something you guys have to do math for. I'm just going to share with you guys what's the purpose of these things. Why do mathematicians care so much about slope fields? For some differential equations, sometimes it's just too difficult or even impossible to find the general solution by integration. So what they do is they make a slope field, and they use the slope field to guess what the shape of the general solution would be. It helps us to estimate values and determine the general shape and behavior of the original solution. Okay, so that's one reason. So for example, suppose a mathematician was unable to identify a formula for let's suppose a mathematician was actually able to know the rate of change for a function, which isn't uncommon. You could know how fast something is changing. But let's say that mathematician wasn't able to figure out what the general solution was. He just knew the rate of change. He didn't know what the actual function was. Well, he could graph all the slopes, and from that, he could think, oh, well, if this is what the slopes look like, then my general solution must be a quadratic, because these look an awful lot like parabolas. Okay, so that's kind of the idea there about why mathematicians might like slope fields. I'm sure they're used for other things too, but for now we'll